The Z transform is a more general transform than the Fourier transform, and we will use it to obtain perfect reconstruction in filter banks and wavelets. Hence, we will now look at the effects of sampling and some more tools in the Z domain. Since we usually deal with causal systems in practice, we use the one-sided Z transform defined as this sum here. It goes from n from 0 to infinity. This is our signal. And here z to the power of minus n. First, observe that we get our usual frequency response, the discrete time Fourier transform, the dTFT, if we evaluate the Z transform along the unit circle in the Z domain when z is equal to e to the power of j omega. What is now the effect of multiplying our signal with the unit pulse train in the Z domain? To see this, we simply apply the Z transform and use our sum formulation for the delta impulse train that is given here. Using delta capital N of n is equal to 1 divided by m, n, and this summation here. And you can see more details about this at our lecture on advanced digital signal processing on lesson 6. It's also available as notebooks and tutorials with embedded videos, so you can check at Guitars AI GitHub or at the UMNL University of Technology homepage at the Applied Media Systems group. There is also a link to the GitHub repository with the Jupyter notebooks, and there are YouTube videos like this one embedded on them. So this becomes this double sum here, and the result is this sum here, 1 divided by n, the sum from k going from 0 to n minus 1, capital X of e to the power minus j 2 pi divided by n k times z. Using the Z transform definition and replacing z by e to the power of minus j times 2 pi divided by n times k times z, we get this relation here. Or in short, we have that x in the Z domain is equal to 1 divided by n, the sum from k going from 0 to n minus 1, and this x is the same like here, x e to the power minus j omega 2 pi divided by n times k times z. There is a mistake here, let's just correct. Z transform definition, and we have here this relation here. This is very similar to the discrete time Fourier transform formulation. We get a sum with aliasing components, just that we don't have frequency shifts for the aliasing terms, but a multiplication of their exponential functions to z. Here we effectively shift the phase, or use rotation, of the complex number z using the complex exponential. This also makes sense since the frequency information is contained in the phase of z, which we see if we replace z equals to e to the power of j capital omega. The next effect is the removal or reinsertion of the zeros from or into the signal. Let's again use our definition. Y of m is equal to x is m times capital N, meaning the y of m is the signal without the zeros. Then the Z transform becomes this relation here. Replacing the sum index m, the lower sampling rate, by the higher sampling rate, n equals to m times capital N, and observing that the sequence x superscript d of n contains the zeros, with x superscript d of n is equal to 0 for n different than m times capital N. This results in, using this index substitution, n equals to m times capital N. Some many typos here, so let's just fix them. This is fixed here. This is also fixed here. So we have this sum here. Observe the 1 divided by capital N in the exponent of z here. And in short, we get that y of z is equal capital X superscript d z to 1 divided by capital N. This exponent 1 divided of capital N of z now corresponds to the stretching of our frequency scale in the Fourier spectrum.